Today we are looking at velocity time graphs. This leads on nicely from the previous work we've done on distance time graphs and acceleration. So what is the point of this lesson? By the end of this lesson you need to be able to draw a velocity time graph. In addition to that, you've got to be able to use that graph to determine loads of information about the journey that you are looking at. This will include working out the acceleration of any motion and also how far the object has travelled during that time. A velocity time graph is used to describe the motion of an object, just like a distance time graph does. However, with a velocity time graph, this time the time goes on the x-axis and you have velocity going on the y-axis. I can't stress enough how important it is that you check the axes of the graph that you are looking at if and when you are presented with this in an exam. People always get these two graphs muddled up, so you must make sure it is clear what you are looking at. Take a moment here to copy down these rules of velocity time graphs because we will use these on the next few slides. So we have our first velocity time graph. What does it show? So let's have a look first at the individual sections of the graph. So for the first 20 seconds we have an uphill slope. Then between 20 and 40 seconds we have a flat line. From 40 to 70 seconds we've got a curved uphill slope. From 70 to 100 seconds we have another flat section. Then between 100 and 120 seconds we have a downhill slope. So let's look at each of these sections individually and work out what they mean and what information we can get from each bit. So section 1, between 0 and 20 seconds, shows a straight uphill slope. This is acceleration. How do we know this? Well, you know from your last lesson that acceleration is quite simply the change in velocity divided by the time taken. Our axes are velocity and time. So quite simply, if we were to work out the gradient of this line, so the change in y, which is the change in velocity, divided by the change in x, we could find the acceleration of this object over this period of time. So the next section shows a steady velocity. This is a flat line between 20 and 40 seconds. So how do we know that it's a steady velocity? Take it across to the y-axis. So the y-axis shows the velocity in meters per second, and if you look along at that section between 20 and 40 seconds, you can see that the velocity is not changing. It is constant at 20 meters per second. I want to draw your attention here to a flat line like this on a distance time graph, because a flat line on a distance time graph means that the object is stationary. It is not moving. Note the difference here. A flat line is not stationary, it is still moving, but it is moving with a constant velocity. The only time on a velocity time graph when the object will be stationary is if that flat line were along the x-axis, i.e. at velocity equals 0. So this next section shows a curving uphill slope. So it's still showing acceleration, but this time the rate of acceleration is changing, as shown by the curve. You can work out the acceleration at any point by drawing a tangent to the line. We described tangents in the lesson on distance time graphs. So if you're unsure, look back at that. And if you're still unsure, drop me a message and I will record something explaining how they work. Once again, we have a section of constant velocity, as shown by a flat line. And finally, the final section of the graph between 100 and 120 seconds shows deceleration. So you've started at a velocity of roughly 40 meters per second, and as you can see the line is sloping downwards, and so the velocity is decreasing steadily to 0 meters per second, where it will come to a stop. So having looked at the different sections of the graph, let's look at the more interesting bits in more detail. So if you have a slope either an upward or a downward slope on a velocity time graph, you can use that to find the acceleration of the object. You know from the previous lesson that acceleration is velocity, change in velocity, divided by the time taken. So working through this example on the screen here, this is a velocity time graph for a race car which accelerates from 0 to 50 meters per second. You can see that there are three sections to this graph. The first section between 0 and 3 seconds, the second between 3 and 6, and then finally between 6 and 12. Because the gradient of each of those three parts is different, it shows that the acceleration in each of those three parts are different. So the actual example is asking you to calculate the acceleration of the car between 3 and 6 seconds. So as you can see, a triangle has been drawn where the gradient of the line is the hypotenuse of the triangle. From there, you join that up to make a right angle triangle, which gives you a change in y, or in other words, a change in velocity of 30 meters per second. And then you can divide that by the change in time, which is 3 seconds. So 30 meters per second divided by 3 seconds gives you an answer of 10 meters per second squared for the acceleration. Okay, so acceleration isn't the only thing you can calculate using a velocity time graph. You can also calculate the distance travelled. The first thing you need to do, and this is what I always say in any area of physics, is think equations. So what equation do you know that is used to find distance? Have you got it? Good. Distance equals speed, or velocity, times time. Oh, what does our graph give us? It gives us a velocity and it gives us a time. So what can we do to find the distance travelled? So this example is asking us to find the distance travelled for this same car that we just calculated the acceleration of between 3 and 6 seconds. And we do that by doing the velocity times the time. And that is also described as the area underneath the graph. So you can find the area underneath the graph in one of two ways. The first way is splitting the graph up into manageable sections. So as you can see in this diagram, it's been split into a triangle labelled as A and a rectangle labelled as B. So to work out the area of triangle A, it's quite simply half times base times height. So the base is 3, between 3 and 6 seconds, and the height is 30, so between 10 and 40 meters per second. Multiply those two together and then halve it, which gives you the area of triangle A, which is 45. The thing you mustn't forget here is you must include that bottom section. Okay, so the distance travelled reaching that 10 meters per second in the first place. So looking at that, that gives us rectangle B. And the area, obviously, of a rectangle is the base times the height. So again, we've got the base, which is 3, and this time the height is just 10 meters per second. So 3 times 10 gives us an answer of 30. Add the two together, so add the area of A and B together, and that gives you the total area underneath that section of the velocity time graph, which gives you the total distance covered by the object. So 45 plus 30 gives you an answer of 75 meters. The second method for calculating the distance travelled by an object is by counting the squares underneath the relevant section of the velocity time graph. This method is particularly useful when the area is being calculated underneath a curved section of the graph where you can't accurately draw a triangle and a rectangle. So having counted the number of squares, you can then multiply that by the distance which one square represents. Right, it's now your turn to put into practice what you have learnt. You've got 4 questions, 2 on this page, 2 on the next page. So please work through them, and then the page following that has got the answers for you to green pen. Do have a good go at the questions first and really make sure you understand what you have learnt. If you haven't, go back through it, and failing that, just send me a message and I will go through it again.